So the first lab, or lab number 7, that we're going to be talking about is parallel flow exchanger, and then lab number 8. Come on. Number 8 is going to be the counter flow exchanger. Okay? So I'm not printing, this is what I posted on Canvas, right? So let me go back to the previous one. So parallel flow heat exchanger means that both fluids are actually flowing in the same direction. And the temperature changes. The hot fluid temperature goes down and the cold temperature goes up. I mean, that's really what happens, right? And then we said that usually most of the heat transfer occurs right there in the beginning, right? And then as you go in the streamwise direction, the heat transfer in this region becomes less, okay? So how do you calculate heat transfer for a heat exchanger? We use the equation Q is equal to UA delta T, you know, where A is just the area that is shared by both fluids. U, we'll come back to that in just a second. Delta T is simply the logarithmic mean temperature difference, right? So if you know the 4 temperatures, you should be able to get the delta T, and obviously when we do the lab, we will know what the 4 temperatures are. The area, we will know what the area is going to be. So the only thing is really U. And remember what U is a function of. Normally, it is a function of 5 resistances between the hot fluid and the cold fluid, which contain convective resistance, fouling, conduction, fouling, and then convective again. But as I said before, the 2 foulings are usually neglected, and then the conduction through the solid wall separating the 2 fluids is neglected. So the only thing we have to worry about is really the H on the inside and the H on the outside. Okay? So this experiment in here is the heat exchanger apparatus, and of course we'll have a great chance to look at it when we are there. What it's going to have is this. It's going to see this bunch of valves in here. You see 2 hoses coming in, right? 1 and 2. One is for the hot fluid, right? So this one, right there. This is the hot fluid coming in. No, sorry. This is the hot fluid coming in.
Oh.
Right there. You know, that's where these are supposed to kind of measure the flow rate, but we typically don't use them. We actually let the water flow into a container. We measure the time to get the flow rate. So this is the hot fluid in. It comes in through here, and then what happens? There is a heater here, right? So even though the water comes in, and we use in here as the fluid inlet, just the hot water tank that we have here, and then we add some heat to it, right? How do we add some heat is just by putting, passing this through a resistive circuit in which we read the voltage and we read the current, right? So V times I gives you the Q in, right? So the water comes in at a certain temperature, and because it receives more heat, right? The temperature at the inlet of the heat exchanger, which is probably going to be this thermocouple here, is going to be high enough. So the water always flows in this direction. It comes in, and then it goes like this, all the way through like this. And then it will exit through here and go back to the sink, okay? So the hot fluid circuit is pretty straightforward, right? Now, to do the parallel flow heat exchanger, obviously, you see here, the fluid is moving from left to right, like this, like that, right? To mimic the parallel flow heat exchanger, this is where the cold fluid comes in, through this right? And then to simulate the parallel flow, what we do is we close this valve, right? Why? Because we don't want the fluid to go this way, right? If we close this valve, we open this one, right? Then what happens, the fluid comes in here and turns this way, right? It turns that way. This valve is obviously going to be closed again, so that fluid doesn't come out, right? So what happens to the fluid that comes in? If all these valves are closed and the only one that's open is this guy, the fluid comes in and goes this way, it goes like that, it goes this way, and comes back like that way. You see, now it's running in the same direction as the hot fluid, except that hot fluid is running into this interior pipe that is really tiny, whereas this one is a thicker pipe. Why? Because it has a jacket, it has an annulus around it, you know, where the cold fluid is running. Now the cold fluid now is going to run in this direction. It's going to run in that direction, come back in here. You probably see that it's running exactly in the same path as the hot fluid. That means it's parallel flow. Then what happens? You come in here, and then what we do is we come back in here. It's going to come out of, because the hot fluid comes out this way, the cold fluid comes out through here, and then this valve was obviously closed. Now what we do is we open this valve, and then we take this hose essentially and connect it here, right? So that the cold fluid comes out and goes to the sink again. Okay. Now to simulate, so this is how parallel flow is going to be simulating. So what data do we typically need when we do heat exchangers? We need mass flow rates, and we need temperatures, right? So a bunch of thermocouples are here. You see, there's a thermocouple there, thermocouple here, there. It's not easy to see here on the picture, but when we will go to the lab, you will see that some of the thermocouples are associated with a hot fluid. Some of the thermocouples are associated with a cold fluid. So the way we did this is we have 3 units in here. This is a digital thermometer that you see at the top, right there. So when we turn it on, it's going to read the temperatures, right? But because you have many thermocouples, you need to go, okay, which thermocouple am I reading? Because it only displays one at a time. So you have, beneath it, you have 2 units, 1 and 2. The first one is it's called a Fluke thermocouple selector. It's a thermocouple selector. So if I need to read thermocouple 1, I just hit on 1, 2, and 3, you know. So all these things are numbered, right? It says the temperatures would be read in degrees C through the Fluke digital thermometer. That's this one here at the top, which is located on the top right of the heat exchanger unit. Below the thermometer are 2 Fluke thermometer thermocouple selectors. This is one of them. That's the other one. The selector that is immediately below the thermometer, that means this guy here, is for the hot fluid. That's why I put it in red, right? It's for the hot fluid in the inner tube, okay? So it says TC. TC, by the way, stands for thermocouple, right? So thermocouple 0 is probably going to be somewhere here. That's thermocouple 0, thermocouple 1, right? Thermocouple 2, thermocouple 3. So for the hot fluid, you have only 4 readings, right? 1 temperature reading before getting into the here, and then 1 at the inner, like T hot in. This is going to be T hot in. 1 is somewhere in between, and the other one is going to be T hot out. Okay. Now the second guy here, the other one, in other words, the other Fluke thermocouple selector, is for the cold fluid. So when we want to read the cold fluid, this is the one that we'll play with. The cold fluid has many more points. In fact, it's got 7 thermocouples. Thermocouple 1 all the way to thermocouple 7, right? So the bottom line, the experiment really doesn't take very long. The problem what we have is that for when we wait too long to measure the flow rate, then the hot water from the tank kind of goes out, and then we get some erroneous stuff afterwards, right? So, thermocouple procedure or experimental procedure, set the control valve to simulate parallel flow, and then we will do it kind of when we go to the lab. Measure the length of the pipe and the diameters of the inner and outer pipe. Those are already measured, right? The outer pipe is 0.0956. Inner pipe is 0.00956. Outer is 0.016, right? And start the hot water fluid and cold water fluid flow. Turn on the heater, and then we measure the mass flow rates for both, right? And then when steady state is reached, right, we record the thermocouple readings for the hot and cold fluid. And done. Okay. Then it's just a matter of stopping the experiment and then mimicking now the counterflow, which is lab number 8, and then taking the same stuff. So this is all the data. The ambient temperature when we read it last time was 17.7 degrees. The pipe length was 1.7 meters. These are the diameters. The hot fluid, we had the mass, we measured 0.589 kilograms in 20.39 seconds. So from taking the ratio of these two should give you the MH. Cold fluid, again, taking the ratio of those two should give you M.C. And the heater voltage is 150 volts, and the current is 5.8 amps. And this is the data, okay? So for the hot fluids, as I said, we only have 4 temperatures. You notice in here that this is the hot temperature coming out of the heater. That's it, in the roof, right? And then when we add heat to it, we were able to get that heat to the temperature to about 51 degrees. And you know what happens to TH, right? As TH in parallel flow goes down, right? Good, I like. Okay, so this is for parallel flow. You have T hot in, you have T hot out, you have T cold in, and you have T cold out. Okay? T hot in is going to be essentially this guy, right? And then as it's running, it's obviously the temperature is going to go down, right? And the temperature cold comes in at 15.8 degrees, and as it's flowing through the pipe, obviously it gets heated up, right? And then when it exits, it exits at a higher temperature.
So what's TC0 then?
What's what?
TC0?
What's TC0? Yeah. TC0 is, so this is where the heat exchanger is. Okay, so this is T hot in, right? And then T cold in comes in through here. But before, so this is the heater. Right? And so this is T, this is that TCO. Okay? Sorry.
Yeah.
Yeah, TC0. Thermocouple 0. So this is the temperature coming out of the water heater. Water heater output. But because this temperature is not really that high compared to the temperature at the tap, right? We wanted to just increase it. So what you do here is you put in kind of a certain voltage, right? And then there is some current I that's going through there. And then the idea is that there is some type of Q in here, which is equal to VI, that we add to the water to heat it up. Okay? So that's why this temperature here comes in at 39.9 degrees, right? And then the moment you get to here, the temperature is going to be at 51 degrees. Okay? At least it's more reasonable. Now you know the mass flow rates, you know the stuff, you should be able to answer all the different questions. It says calculate the power delivered to the heat up the water heater. If you know the voltage, you know the current, you can find what Q is, right? And then calculate the heat absorbed by the hot water as it exits the heater. Remember here, this Q, this VI should be equal to mass flow rate of the hot water times Cp of the hot water times this temperature minus that temperature.
Wait.
MC delta T.
Say that one more time. What is?
So Q in
Yeah.
should equal,
Yeah.
or approximately, M dot H CPH, right? T hot N minus, maybe I should call it TC1 minus TC0. Makes sense? I mean, if the water is coming in through here,
Yeah.
its temperature has gone up,
Yeah.
right? That temperature went up because of the heat added by this voltage and current. Okay? Then from there you can figure out what is the efficiency of the heater. In other words, out of that heat that's generated by the heater, which is Q heater, is essentially equal to just VI, right? Once you calculate the energy that is used up by the water, how much energy did it take to raise the temperature of the water from 39.9 to 51, right? That should tell you how much, what's fraction of this it has used, and then from there you can get the efficiency of the heater. Did all the heat go to the water, or just part of 90% of it, or something like that? So that's what the efficiency of the heater. Calculate the heat lost by the water through the heat exchanger. We know what that is, right? Calculate the heat gained by the cold water through the heat exchanger. So in other words, what you're trying to do, calculate these terms, right? And comment on the energy balance. Are they the same? Don't expect things to be exactly the same. This is an experiment after all, right? But at least are they kind of in the same neighborhood?
For cross flow, they should be close, right?
This should be
Pretty
close,
close.
but you have to keep in mind, that you have a hot water flowing through here, you have cold water that is flowing through there, you know, through a certain kind of thickness, right? So, but this is not insulated.
Oh.
In fact, when you touch it, you find that, darn it, it's a little bit warm, right? So what does that tell you? Some of that heat is gained.
Yeah.
Okay, that's part of the error analysis.
In our design project, can we just make an assumption that everything's insulated?
Well, you know, when you do the calculation, that's the basic assumption, is that those two have to be the same, because
Okay.
for these two to be the same, that means
That you're not losing anything.
that is everything is insulated. But obviously, if you find that it is not, then you're gonna go, why isn't it, right? Then maybe that's one of the reasons.
Okay.
And log mean temperature difference, that should be easy to find. Calculate the experimental value of QA. So that's what you do. Remember, the only things is you need to define what the HI is and what the H out is, right? What is H in here? And what is H in there, right? And calculate, here we go, compare it to the experimental value, and that's it. So, kind of in general, what those things are. And when we go to the other one, that's almost exactly the same. Number 8, the only difference in number 8 is that it is counterflow, right? So this is lab 7. lab number 8, now the hot fluid is coming in like this, as T hot in, and this is T hot out, right? But now it's counterflow. What's going to happen is that the temperature of the water coming in is through here. And this is going to be T cold out. So you have kind of a decent temperature difference throughout the entire length of the path. And as we know, the efficiency, of a counterflow exchanger is better than that of the parallel flow exchanger. So what do we do through here? It shares a lot of parallel things with a lot of common things. The equations are exactly the same. Q is calculated exactly the same way. Delta TLM is the same thing, except that remember when we talk about delta T1, this is location 1, that's location number 2. This is location 1, this is location 2. So obviously this distance in here is delta T1. This distance in here is delta T2, right? Just like in here. This is going to be delta T2, and this big guy is going to be T1. So the unit is exactly the same. The only difference that we make when we do the second experiment is we reroute the flow. You see, the hot fluid still is going to come through here. It gets heated up there, and then it's going to go from left to right on the top, and then it's going to turn around, and then go back this way, come back in here, and then come back to there, and then go out to the sink. Okay? So the circuit of the hot water does not change. Now, to mimic the counterflow, obviously the cold fluid still is going to come through here. Now, what I need to do is close up this valve. You probably guess why this outlet is already here, because we always do parallel and then counterflow. So that means the way it is now, it's probably counterflow. So it comes in. So what this does is we make sure this valve is closed here. And if this valve is closed, that means this fluid is forced to go in which direction? To the right. And we open up this valve, right? And then we close up this valve. So this guy is closed. So what happens? The fluid comes in, it's closed through here, so it's not going to do anything. The only path it has to go through is this way. And then up, right? And then come back, and then it enters the jacket right there. As it enters the jacket, now it has to flow in this direction. See? Now it's going opposite what the hot fluid is doing, right? And then it continues on this side. Now, what does it exit? It comes in, then it exits through this guy, up in here. Oops. It comes in like that, and then comes in like this. Remember, this valve was closed, right? And this one will be open, so it's going to come out through here. So cold in, cold out. And again, the thermocouples are exactly the same thermocouples that we need to be reading, right? And you guys need to probably take a picture of that to just see where the thermocouples are. And this is the data, okay? Ambient air was the same, the pipe length was the same, inner and outer was the same. We did not use the same mass flow rates because we had to turn everything off and then do the same thing all over again. We did the same voltage and the same current because we had a variac that we were able to move. But then the hot fluid comes in at 33, right? That's before getting heated up. You probably go like, why did we have here 39.9? Why do we have 33? Yeah, because we have used up our downhole hot water.
Oh, because now the tank is getting full.
Yeah, the tank is, you see, that's the downside of this experiment. You see, when you do both of them back to back. But in any case, the temperature was 33, But then, after the heater, right, we were able to push that temperature up to 45 degrees. And you know what's going to happen? The second temperature is kind of right in the middle, so it's going to be 39.9, and then it goes down to 34.9. The cold temperature comes in at so why is this temperature high? Because T cold in now is on the other side, see?
Oh,
So
okay.
this is where the hot temperature, where the cold temperature is coming in. I mean, the thermocouple did not change. So for the parallel one, right, the outer one becomes the inner one for the counterflow. Okay, it's easier to see when you see the So the temperature comes in at 15.4, and you know what's going to happen for the cold temperature. It's going to start low, and it's going to start gradually increasing. Okay, so it starts at 15.4, goes 22.1, et cetera, and it ends up at 29.2. Okay, so the trends are there, right? And the idea in terms of the questions are exactly the same as the other one. Find what is the power delivered by the hot water, which is simply V times I, right? And then from there, calculate the heat absorbed by the hot water as it exits, and then the efficiency and the rest. So that's what these experiments are. So we're going to use this data. What we need to do now is just go step into here just to see how that is working in case you have any questions. And then we call it a day.
It looked bigger in the picture.
It looks bigger in the picture.
Yeah, there's a little setup over here.
Okay, so after you take the picture, let me just explain the situation there. So this is the hot water. See here? It says, doesn't say anything. All right, it's supposed to say hot water in. Okay, so it's this clear guy, right? It's the clear guy which is connected to this guy, right? And then it says hot. Okay, so that's directly connected to the hot water thing there. So the hot water comes in through here. That's the valve. We just open it. So the hot water comes through here, and then this is the heater, right? And the heater is controlled by, that variac there, in which we usually set it up to a certain voltage and a certain current, right? Once we read those, then we are fine. This is the original setup that reads the temperature. That means you just have to cycle through those, but it's not digital, so we had to kind of go back and get these units there. And so what happens is these guys are all thermocouples. Okay? So for the hot water, let's concentrate on just the hot water. This is the temperature that just comes in from the hot water. Water here. Before getting into the heater, this is thermocouple 0. This is what TC0 is. Okay? We called it TC0 because these numbers are already there, right? TC1, and then there is TC2, and then there is TC3. See, 1, 2, 3 numbers, but it's kind of bold around it.
Okay, there's.
Because there is also number 1, so the big numbers are for the cold.
Okay.
The tiny ones are for the hot. Okay? So how many temperatures do we need are we able to measure for the hot fluid is just this inlet temperature, 1, number 2, number 3, and number 4. That's why we have 4 temperatures, TC0, TC1, TC2, TC3, okay? And for the cold fluid is going to come through here. It's always, see it says cold in, right? It comes through here. Now, I bet this is, I don't know if this is open or closed. Well, I can probably set it to, if we want to set it, let's say, if we want to set it to parallel flow, okay, what do? We have to close this guy. And then we have to open this guy. Okay, so that's closed. And then we come in, so the cold fluid comes in through here, comes in through there, enters the jacket, right? And then flows, and then flows there, come back through here, see? And then come back through the jacket. Now it has to decide where to go. Obviously, because this guy is already closed, it can only go through here. So what we typically do in there, so that we don't make a mess, is that the cold out has to be switched to here. Does that make sense? And obviously have to make sure that this guy is open too. There you go. So here we are simulating the parallel flow heat exchanger. Okay? This simulates a parallel flow heat exchanger. And before we start the experiment, what we typically do is we turn on this guy. That's going to read something weird, right? I bet that the ambient temperature is about this much. And now, remember what this one does? This one measures the hot temperatures, and this one measures the cold temperatures, okay? We know that for the hot temperature, we only have 4 thermocouples, TC0, 1, 2, 3, right? So if you need to read the inlet temperature, just click on that. And then temperature number 1, temperature number 2, temperature number 3. What do you think I'm going to read when I take this one? Probably it's going to give me an error message because there is no thermocouple that is attached to it, right? No, that is wrong.
They're not switched.
Let me see. Something is not right. Unless, maybe I didn't click that. Oh, okay. So I have to kind of turn off this guy, you know, so it's only this guy that is, I think what it was doing was I had both of them
it's
at
going
the
over
same
check.
time, you know, so it's not normal. So this one is on, right? So this is the temperature of the fluid in here. And then this is this temperature right there. And then that temperature 2 should be pretty close. You know, give or take a tenth of a degree or 2. And then that's the temperature at 3 right there, right? 3 right there. And then obviously in 4, because I have nothing, 5 I have nothing, 6 I have nothing, etc. I'm not reading anything, right? So as I do that, we read those 4 temperatures, and then what do? We close up this guy, and then we come and read this one. Now, why am I reading out of channel, right? Because there is no thermocouple 0 for cold fluid. The cold fluid only starts with thermocouple 1, sequentially all the way to 1, 2, 2 is pretty darn close to 1, right? 3, 4, 5, 6, and 7. Okay? So then what we do, once we have reached steady state, the only thing we do, go, okay, 1. Now something happened in here. Okay, so thermocouple 1, somehow it's not working very well. 3, 4, 5, 6, 7. Okay, that's TC out. This one should be out of channel. And then they should be out of channel because we don't have thermocouples associated with them. Once in a while, we do have one thermocouple, like in this case. This one somehow does not register very well.
That's the hot one, right? So it should
No,
be.
that's not the hot one. Oh, yeah, sorry. Yeah,
Yeah.
it's this one. Yeah. This one is not kind of showing up, but then we say, well, 2 is pretty darn close to 1 anyway, so let's call it that. So that's really what it is, you know. Let's see. We can just maybe just kind of run something, you know. We're not going to take data, but just maybe I'll do this for you guys, and then I'll do counterflow for the other ones, you know, just to kind of see how it works.
Mm-hmm.
So the way it works is you turn on initially the hot water. I hope I'm not going to make a mess because I haven't tested this. Here, so we have hot water that is flowing. Right? Now the only thing that's flowing is hot water, right? So maybe I should probably be looking at this one. Right? So the water is coming in at 24.8, 24.5. So what am I reading?
TC 0.
Well, I hope there is hot water in the tank.
Does it feel hot?
24.3, 4, 5, 6. You can see that
Yeah,
something
it's
is
gone.
heating up.
Yeah.
Right? Now, it's not great, but it is heating up, and it's probably going to reach a certain. But if I go to temperature number 2, it's probably going to be the same thing, right? That's 0. That's 1.
2 is hotter.
It should be different, right? Because
It should be.
T0 is before the heater and T1
That's-
is after.
Yeah. That's what's going on?
1 is before.
So,
Oh, that's 0, right?
That's 33.8.
And then 1 is after the heater.
Uh,
It's higher.
Is it close or is it higher? It's a little higher.
It's higher.
How is it? How come it is higher?
Well,
Because
because
that
it goes
thing
through the
is
heater,
off.
right?
Well, 1 and then 2, you know, those things should be.
Well, it's
Maybe.
that here, right?
So it's 1. Yeah, it's 1 and that's 2. Yes, that's right. Now that's 2. It's 39.8. 1 is 39.9. That means I'm at 1.9 in here, right?
Right.
And then before the heater,
Should be colder.
well, but my heater is not turned on.
Oh,
No.
well,
See, that's
and
not,
I don't know, friction or?
even though, you know, it kind of seems like it is a little bit hot, but what bothers me is that I don't register anything in there, you know, it's still off power-wise.
Yeah.
But when I touch in here, I sense that there is a, unless it's just the water, but I doubt it, you know. $40. Yeah. It's not that big difference. 40.4. 38.6. For more practical purposes. I don't know why it's warmer though. It's kind of weird. But what we typically do is we do this. We turn on this guy, right? And then we put in at 150 or something like this, right? Now, if I go to temperature 1 now, what you would probably notice is that this temperature should be going up, because now you're heating up the stuff, right? Now you see a big discrepancy between that temperature and this temperature here, which is pretty limited, right? I think it stayed at about 38.7, right? But now, even though this is stayed at 38.7, what's happening now for that temperature, 44.9, 45, right? And then it's waiting game. Then you have to wait until it reaches steady state, okay?
Oh, wow.
And the temperature there should be maybe a little bit close to that one, because you're not losing anything. There is no cold water.
Yeah, cold water going on.
Okay? And in fact, temperature number 3 should also be pretty darn close. Now, after we do this, then what we do is we turn on the
Cold water.
cold water. Now, obviously, here what we do, knowing what this output is, while we're waiting for steady state to occur, we do our measurement of the flow rate, you know, to kind of gain time. Now, what I do is I come back in here and do my my cold water, because so far I don't have any cold water running through there, right? If I do cold water,
Oh,
ooh,
yeah, a little bit of a leak.
what's happening there?
Yeah, it's leaking up.
But it's leaking. Darn it.
I think your cold water out is leaking. Or is that? Oh.
Well, that's not good.
Call a plumber.
I don't know if it's this. I think it's leaking through here, unless it's this. Cold water in was fine, but what the heck? Let it leak a little bit. Let's see what happens. Yeah. Yeah, that's not good. Well, I'll have to fix that somehow. So what we do on that one is we run it, measure the flow rate, and then at the same time make sure we cycle through these temperatures. So I'm glad we have the data already
Yeah.
taken care of, because maybe when we moved it because last time we did it, it was in that lab, then we moved it back in here. So I need to spend some time looking at it later on. Okay, so any questions about this? I mean, after this is done, then what we typically do is we turn everything off and we switch the circuit, right? The hot circuit stays exactly the same, you know.
Yeah, it's
Let me
just
turn
cold
this
circuit.
off. Makes sense. So what we do is we close this valve now. We open this valve, right? And we close this one, right?
Mm-hmm.
And put this guy out, because now the cold fluid is going to come back through here. And so because this is closed, the cold fluid is going to come through here, through there, enter the jacket at this location, right? Now it's flowing opposite. See, it's going to come through here.
Mm-hmm.
That's going to opposite what the hot fluid is doing. It's going to go up. It's going to reach this point, then it's going to say, I need to get out, right? It's going to come back in here. And because this guy is closed, right? We closed it. Then we have to open this guy. Then it's going to come down in here with this guy in, and then going back to the sink that allows us at least to measure the flow rate. And that takes care of the counterflow. So the data, you know, is not difficult to take, except that usually if you start from the parallel and you go to counter, the darn thing is already kind of depleted somehow.
Right.
That's why the temperatures, but it kind of gives you some idea. You see the temperature trends, and that's really what it is. And that concludes the experiment.
So for the Q, is that you just need the voltage and the amperage for the Q in?
Yeah, for Qn, all you need is voltage times the current,
Oh,
and the voltage was given to you,
Mm-hmm.
and the current was given to you.
okay.